Hello everyone, just a second. Hello everyone, welcome back to the channel, welcome back to the learning field. Just a second. So this is the session for the questions paper discussion on GATE exam. Okay, GATE 2017 LPP. Okay, GATE 2017 LPP. Okay, so in this session we are discussing this session the GATE 2017 LPP papers. Okay, so let's start, and before starting I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and subscribe the channel. Okay, and one more thing is that we are already solved the questions paper the LPP section of GATE 2020, 2021, 2020, 2019 and 2018. Okay, and in this session we are solving 2017 section. So if you want to solve these questions, or if you want to do the solution, or if you want to see the solutions, then you can check the playlist of GATE mathematics and what and the GATE LPP lectures, which is already available in the channel. Okay, and the link will be in the description and also here in the I tab. Okay, and one more thing is that the lecture series for the GATE LPP section is also available. Okay, so you can check the theorem section or theory part also. Okay, the GATE complete lecture series. Okay, you can check it. So now we are going to the question number 24. Okay, so the question, there are 4 questions in GATE 2017. Okay, 1 mark, 1 mark, 2 mark and 2 mark. So there are total 6 marks comes in GATE 2017. 1 plus 1 plus 2 plus 2. Okay, so you can get easily the 6 marks. Okay, the question says that consider the linear programming problem, that is the LPP, maximize 4x1 plus 6x2 subject to x1 plus x2 less equal to 8 and 2x1 plus 3x2 greater equal to 18, x1 greater equal to 6, x2 is unrestricted in sign. Okay, then the LPP has. So this is a very easy problem. We just draw the graph of this LPP. Okay, so suppose this is the graph x1 and x2, x1 plus x2 equal to 8. Suppose this is, that is 80 point and 08 point. Okay, so this is suppose the line 80 and 80 and 08. Okay, this is the first line, which is x1 plus x2 equal to 8. The second one is 2x1 plus 3x2 greater equal to 18. That is the line is x1 by 9 plus x2 by 6. This is equal to 1. Okay, so this is the suppose 9 point and this is suppose the 6 point. So we just draw these lines by this, and then if we calculate the intersection point, that is this point, we get what from the first 2 point. This point gives 2x1 plus 3x2 this is equal to 18 and 2x1 plus 2x2 this is equal to 16. If we subtract, then we get x2 equal to what? X2 equal to 2. Okay, and x1 equal to what? From 1 we get x1 equal to 8 minus 2 is equal to 6. So 6, 2 is this point, 6, 2. Okay, now we draw the third line x1 greater equal to 6. That is x1 equal to 6, that is this is the line and this is the point 6. So the line passes through this intersection also. Okay, so this is the line x1 equal to 6. Okay, so these three this is the line, and if we now give the region, that is x1 plus x2 0 0, if we put 0 0, then this is satisfies. That means this side is the region or the first line, this one, and now the second one is 0 0. If we put, then this is the outside of the region, 0 0 greater equal to 18, which is first. So this is this region. Okay, and the third region is what? x1 greater equal to 6, that is this 0 0, that is 0 put, that is this is the region. Okay, so this is the region, you can say common region. No, I think sorry, this is the line and this is the line. Okay, so from this line this, and from this line this, from this line this, so this this point is only the region. Okay, this point is 6 2. So 6 2 is only the point. Okay, so 6 2 is only the point in which the LPP gives the optimal solution. Okay, otherwise there is no point in any region. Okay, we don't get any region, we do not get any region. So this point 6 2 is only the solution of the LPP. So option A says that no optimal solution, this is false. Only one basic feasible solution, that is optimal. Yes, this is correct. This is the correct option, 6 2. We get only one point which is basic feasible, and that is the optimal solution. Okay, and we can get the maximum value at this point only. So more than one basic feasible solution, no, this is not correct. Infinitely many solution, this is also not correct. So option B here in this problem, option B is correct option. Now we go to the next problem. The next problem is question number 25. Question number 25 says that for a linear programming problem, LPP and its dual, which one of the following is not true? Okay, so which of the following is not true? So the first option says that the dual of the dual is primal. Yes, this is true statement. So this is not true or not true. And the primal LPP has an unbounded objective function, that is unbounded objective function, then the dual is infeasible. Yes, this is true, because if the primal has primal problem has unbounded, then two cases may occur. Okay, one is what? The dual is infeasible, or dual has unbounded solution. It can maybe occur. Okay, UBD, unbounded. Okay, so these two cases may be occur if the primal problem is unbounded. Okay, so it says that if the primal problem is unbounded objective function, then the dual is infeasible. Yes, this is correct. It maybe happens. The third option says that the primal LPP is if the primal LPP is infeasible, then the dual LPP must have the unbounded solution. Yes, it has unbounded solution, but this must not have, because other cases may be possible. Okay, because if this is only unbounded solution, then this case we mistake. Okay, this case is not also you can, this case may be occur. Okay, so this says that must have, so this is not true. Okay, this is not true. Therefore option C is not true. If the primal LPP has a finite optimal solution, then the dual LPP also has finite optimal solution. Yes, this is true by the fundamental theorem of LPP. Okay, so therefore not true option is option number C. Now we go to the next problem. The next problem says that consider the following what? Consider the following transportation problem. The entries inside the cells denote per unit cost of the transportation problem. Okay, of the origin. So here we can apply first the northwest corner method, then we can apply row minima, then we can apply column minima, and then we can apply matrix minima number 4. Okay, and up to we improve the methods, we also get the improved initial basic feasible solution here. So in case, and VAM is the most favorable method you can get, and VAM gives the most improved initial basic feasible solution, but VAM is a big method. There are various number of calculations. Okay, so we apply here the matrix minima method. Okay, so we just write the matrix of the cost matrix. We just write the cost matrix. Okay, this is a 3 by 3 cost matrix. There is 4, 3, 6, 7, 10, 5, 8, 9 and 7. Okay, and 10 demand is 10, 30, 60, 20, 30 and 50. Okay, now we find what is the matrix minima method. We find the minimum most element from all over the matrix. So 3 is the minimum most element, so there is the first allocation. Okay, so the first allocation is minimum of this 20 and this 30. Okay, minimum of 20 and 30 is 20. So this the demand, the supply is exhausted from here. Okay, and there is remaining 10 units. Okay, now if we find the next minimum element, the next minimum element from all over the matrix is this 5. Therefore we allocate here, and we put here the minimum of this 30 and this 60, which is equal to 30. So this is exhausted now, and here 30 units remaining. Now the next minimum element is this 7, therefore we allocate minimum of 50 and 30. Minimum of 50 and 30 is 30, so therefore this is exhausted and there is remaining 20 units. Okay, the next minimum element is 8, and here minimum of 10 and 20, we put allocate here 10 and then we allocate here 10. Okay, therefore we get the these allocations. Okay, 1 2 3 4 5, so we get 5 allocations, and we know that the number of allocations is equal to m, maximum allocations is equal to m plus n minus 1, that is here 3 plus 3 minus 1, so this is equal to 5. Therefore this is a non-degenerate basic feasible solution. Okay, now we check whether this initial basic feasible solution is a optimal solution or not. To check the optimal solution by Modi method, okay, or Modi test you can say. So we just write the table once again with the allocations. Okay, 4 3 6 7 10 and 5 and 8 and 9 and 7. Okay, and the allocations are here, sorry, here 20 units, here 30 units, here 10 units, here 10 units, and here also 30 units. Okay, now we solved, we find what? We find all the uij and vij by using this formula, ui plus vj equal to cij, where cij is the cost. Okay, so we find all the uij's and vij by putting the ui, one ui, this is or vj equal to 0, in which the maximum allocation is occurs. Now we see that in the third row the maximum allocation is occurs, that is there are all 3 allocations which are the number of maximum allocation. Therefore we put here u3 equal to 0. That means if we put u3 equal to 0 and now calculate the what? We now calculate the vij by using this relation, that is, see, 0 plus vij, this is equal to 0 plus vij, this is equal to 8, therefore this is equal to 8 we get. Okay, since this is the cij cost, this is 9 and this is 7, just write the upper side. Okay, just a second. So this is 8, u1 equal to v1 equal to 8, v2 equal to 9 and v3 equal to 7. Okay, because 0 plus 8 is equal to cost, 0 plus 8 equal to cij, 0 plus 9 equal to cij, and 0 plus 7 equal to cij. Now this is one allocation, so this is 3, cost is 3, therefore if we put here minus 6, that is ui equal to this and vj equal to this gives the cost minus 3. Okay, this is the value of v1, v2 and v3, and this is the value of u1 and u2 and u3. Okay, we assume u3 equal to 0, therefore this value of u3 is what? This is 7, this is 7, the v3 is 7, therefore we put here minus 2. Okay, so 7 minus 2, this is equal to 5. Okay, therefore these are the values of uij for the allocation. We calculate this for the given cell allocation. Okay, now we find what? We find the delta ij, which is equal to cij minus ui plus vj for the non allocative cells. Okay, so this gives, if this delta ij, all delta ij's are greater or equal to 0, then we say that the optimal condition is satisfied for this initial basic feasible solution. Okay, so now we find this one first. Okay, so this means 4 minus 8 minus 6. Okay, 4 minus 8 minus 6, which is equal to 2, which is greater or equal to 0. So this is equal to 2, which is we write this 2 in a circle. Okay, for this we get what? For this cell, so this is equal to delta 1 1. Now if we calculate for this non-allocated set, which is equal to delta 1 3, this is equal to what? This is equal to cij means 6 minus what? Ui plus vj means, ui means minus 6 plus vj means 7. So this is equal to 6 minus 1. So this is equal to 5, which is greater or equal to 0 again. So this is 5, which is greater or equal to 0. Now we calculate for this. So this is delta 2 1 for this cell, delta 2 1, this is equal to what? Delta 2 1 equal to 7 minus minus 2 plus 8. Okay, so 7 minus this is 6, this is equal to 1, which is greater or equal to 0. This is 1, which is greater or equal to 0. For this cell we get delta 2 2. So this is equal to 10 minus what? Minus 2 plus 9, minus 2 plus 9, this is equal to 10 minus 7, which is equal to 3, which is also greater or equal to 0. So 3 is greater or equal to 0 again. Therefore all the delta ij's, see, all the delta ij's are greater or equal to 0. Therefore this is the optimal solution. You have to check this optimality condition for any method, for any IBFS. Okay, so this is the optimal solution. We can say the initial basic possible solution is the optimal solution. Therefore the cost is equal to what? Cost is equal to this 2 in 20 into 3 plus what? 30 into 5, 30 into 5 plus 10 into 8, 10 into 8 plus 10 into 9 plus 30 into 7. Okay, so this is the optimal cost, and this is equal to what? 60 plus 150 plus 80 plus 90 plus 210, 150, 360, 450, 450 plus 60 plus 80. I think this is equal to 590. Yes, 590 unit is the optimal solution. Therefore the optimal transportation cost is 590 units. Okay, so this is the solution of the problem. Now I go to the next problem. Problem number 55. This is also a 2 marks question. Okay, the question is that consider the linear programming problem. Maximize k equal to kx1 plus 5x2 subject to x1 plus x2 less equal to 1 and 2x1 plus 3x2 less equal to 1. Okay, so x1 star, if x star equal to x1 and x2 star is an optimal solution of the above LP with k equal to 2, then the largest value of k for which the x star remains the optimal equation, optimal equals. Okay, so we first write the dual of this problem. Okay, so the dual is what? Suppose the dual variable is y1 and y2. So the dual means minimize y1 plus y2. Okay, subject to what? Subject to x1 y1 plus 2y2, y1 plus 2y2, which is greater or equal to k, and what? And y1 plus 3y2, y1 plus 3y2, this is greater or equal to 5. So this is the dual of the given primal problem. Okay, now we first solve for the primal problem. Okay, we first find the solution of the by using the graphical method. So suppose this is 1 1 1 0 and 0 1. The first straight line x1 plus x2, this is equal to 1, and 2x1 plus 3x2, that is x1 by 2 and x2 by 3. Suppose this is, so this is 1 by 2 comma 0 and this is 0 comma 1 by 3. Okay, this is another line. The line is what? 2x1 plus 3x2 equal to 1. Okay, now if we put 0 0, then this gives this side, and this is also gives this side. Therefore this is the optimal solution. This is the complete region, and the 3 points are half 0 0 half, and the 3 region is 0 0 half 0 and what? 0 comma 1 by 3. Now we calculate the objective function, that is kx1 for the value k equal to 2. Okay, that is this 2x1 plus 5x2. Okay, so for 2x1 plus 5x2, this gives 0, and this gives what? This gives 1, and this gives 5 by 3. Okay, so this is the maximum solution. 0 comma 1 by 3 gives the maximum solution. Okay, this is the maximum solution. So if 0 1 by 3 is the maximum solution, then what happens? Then and 0 is what? 0 is the now we apply the complementary slackness theorem. Okay, if the this is non-zero, the primal problem optimal, in the optimal form the primal variable is non-zero, then the dual variable dual constant is equality. Therefore the second constant of the dual is equality. That means what? y1 plus 3y2, that is y1 plus 3y2. I think this is the optimal, right? 0 1 by 3 2, oh sorry, just a minute, k equal to 2, half 0 and 0 half. Right, you are right. So 3y2, this is equality. So this is equal to what? This is equal to 5. And one more thing is that we now put this value to this constant, okay, whether to check whether the constant satisfies the strict inequality or not. So if we put 0 1 by 3 here, 0 1 by 3, this gives strictly less than 1, 0 plus 1 by 3, and just a minute, if we put 0 1 by 3 here, then this gives less equal to 1, okay. So this is the strict inequality, okay. That means the corresponding dual variable is 0. That means the first dual variable, since the first constant here satisfies the strict inequality, therefore the first dual variable is 0. That means what? y1 equal to 0, okay. So if we put y1 equal to 0, we just get so y2, this is equal to 5 by 3, okay. So we get y2 equal to 5 by 3 from here. Now from the first dual variable, what? y1 plus 2y2 is greater or equal to k, okay. y1 is 0, so 0 plus the value of y2 is what? 5 by 3. So 2 into 5 by 3, which is greater or equal to k. So this is implies k is less equal to 10 by 3. We have to find the largest value of k. Therefore the value of k should less from, this is the largest value, okay, 10 by 3. So k less equal to 10 by 3. That means what? 3. So my largest value of k is what? 10 by 3. Rounded up 2 decimal places, that is equal to 3.33. Okay, so this is the correct answer for the problem 3.33. So these 4 questions are from the GATE 2017 section LPB. Okay, so if you like the content, then please give a like to this video, share with your friends, and subscribe the channel. Thank you friends, see you again in the next video.